What's going on, everybody? This is Mr. Diamond, and welcome to Chapter 6, Chemistry Calculations. This is Chapter 6 of General Chemistry. How do we do math in chemistry? Congratulations! You have successfully made it to the math portion of the class. I know some of you were dreading this moment and some of you were excited about this moment, but we are now at the point where for the rest of the year, we will be doing math. This is your last break from having to know any of the naming rules. So this is your last chance to brush up on study on them. This is the last chapter where that is not relevant. After this, you will need this chapter, naming, and all of the equation stuff from last chapter all shuffled together for the rest of the year. If you like math, these next chapters should be good for you as long as you're comfortable with your naming and your formula stuff. If you do not like math, this is the time where you're going to have to start focusing, paying a lot more attention, and asking more questions in class when they come up. This entire chapter is pretty short. It's probably the shortest chapter all year, and it's just going to be kind of quickly running through how we do math and chemistry. It's also going to give you a chance to have a little bit of a test buffer if you're worried about your grade in the class. This test may not be easy, but it at least is going to be simpler than the other stuff that we're going to be doing later on. You also should make sure you'll be bringing your calculator to class from this point on if you haven't already. So we're going to start with something pretty easy. In section 1, we're just going to talk about numbers and figures, and more specifically, we're going to begin with scientific notation. You are hopefully familiar with this. Some people I think have said they've talked about it in math classes. You may have talked about it in previous science classes, but scientific notation is the way we represent very big or very small numbers in science. It's just more efficient to write them in scientific notation than it is to write really big numbers, and we'll talk about why whenever we get into some of the later sections of this chapter, but and in class we'll actually do a thing on the board that demonstrates this. But for those of you who are at home and watching this, one very common example of a number that is actually super important in chemistry is a number called Avogadro's number. We're going to talk about it next chapter, and that number, if you didn't say it in scientific notation, would be 602 zero 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 zero, which would be absurd. And instead, we write it as 6.02 times 10 to the 23rd. It's just way easier to do that than to list off all of the zeros every time we use it. So how do we use scientific notation? Well, negative exponent values are when a number is less than 1. So 1.0 times 10 to the negative 1 is the same thing as 0.1, which is less than 1. Negative exponent does not mean the number is negative. Positive exponents are used when the number is bigger than 9.99, repeating, so infinitely 9. So if it's 10 or higher, basically, you're dealing with a positive exponent. And then if the exponent is between, or if the number is between 1 and just below 9, anything above 1 and anything below 10, anything in that range, you get to use an exponent of 0. But normally you're not using scientific notation for those numbers. We will in this class a couple of times just because you want to get some practice with it, but in real life you're not really going to use those for that much. So we've got a couple of examples here. We're going to translate the following numbers to scientific notation. Now I'm going to do this mentally out loud. We're not going to use switch to a video where I'm going to do the examples of these. So the first thing you should notice about this first number is that it is below 1. It is a decimal number. It is very small. That means our exponent needs to be negative. The easiest way to figure out what your scientific notation is to count how many decimal places you would have to move to get it so that it's in this format, where there is a number, only one number that is not 0 before the decimal, and then all of the other numbers that are not 0 or other than this first one are after that number. So if we go back to this example here, the first thing that isn't 0 that we would care about would be this 6. So we want to move our decimal so that it is right between the 6 and the next number, which would be 2. Those are our first 2 digits that are not zeros in the number, although the second one could be 0. And we're going to have to move our decimal 1, 2, 3, 4 to the right. If you're moving a decimal to the right, or you could just remember that if it's a number that's smaller than 1, your exponent has to be negative. So we would say that this number here would be 6.230 times 10 to the negative 1, 2, 3, 4 times 10 to the negative fourth. Now that doesn't really save us a whole lot because that's going to be probably about the same number of punches in a calculator as this one, but the next one will save us a little bit of time. So we have 2, 3, 4, 9, 1, 0, 0, 0, 0, 0, 0, 0, or 234, let's see, that'd be hundreds, thousands, millions, billions. 234,910,000, or million. There we go. We're going to do the same idea. So first, is this number bigger than 1, or bigger than, smaller than 1, or bigger than 10? In this case, it's bigger than 10, so we're going to be using a positive exponent for it. This time, though, this decimal was clearly written for us. It was right here. This one doesn't have a decimal, but we know that the decimal would have gone right here. It would have been at the very end of the number, so we're going to count from there. In this case, notice that here we went to the right. Here we're going to go to the left. So that's another sign that you're dealing with a positive exponent. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Again, you want it to be between these two pieces right here. So we'll get 2.3491 times 10 to the, it's positive, and it's again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2.3491 times 10 to the 11th. Again, that one saves us a little bit of time. If there was less numbers right here, it would have saved us a decent more amount of time. So here we go. We have 2.30 times 10 to the negative fourth, and then, or 6.230 times 10 to the negative fourth, and 2.3491 times 10 to the 11th. So to go backwards, you may also be asked to do this, taking a number in scientific notation and then taking it out of scientific notation. So here I have 1.435 times 10 to the 0. Times 10 to the 0 means we move the decimal 0 places. You don't move it at all. So it's actually just 1.435. For the other ones, you have to go the opposite direction as when you were counting it, which is a kind of a more difficult way of remembering it. But the way I like to remember it is I go, okay, 9.686 times 10 to the 11th. That is a positive exponent, and positive exponents are used for numbers that are bigger than 10. So we need to move our decimal a direction that will lead us to having a number bigger than 10. What happens if we move the decimal to the left? Well, the first move to the left gives us 0.9686. And if we keep doing that, the number's only going to get smaller. It's a positive exponent. We don't want to do that. So we're going to have to move it to the right instead. So it's going to have to be 1, 2, 3. And then we run out of space to move it, so we're going to have to start adding zeros. 4, 5, 6, 7, 8, 9, 10, 11. So that's 1, 2, 3. And then there's going to be 8 more zeros added to the end of this number to turn it into a normal number. And if we go over here, we should indeed have 1, 2, 3, 4, 5, 6, 7, 8 extra zeros. Because again, if we would have done this backwards, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 spaces the decimal had to move. We moved it 11 spaces to the right, so we got this number. All right, that's for scientific notation. Next, we're going to be talking about what's usually going to be the next bane of your existence after polyatomics and naming, but we'll get to that in the next video. In the meantime, though, this is Mr. Diamond. If you have any questions, please shoot me an email. Otherwise, have a great rest of your day, everybody.